In this video, I will be discussing my Bachelor in Engineering thesis. This looks at low-energy internet using software-defined networking. It has been estimated that the internet and computer networks use approximately 1.5 to 5.5% of global electricity. This figure depends on whose figures you read and whether they take into account the energy costs associated with the end-user terminals and manufacturing of all the hardware used. This roughly breaks down as 37% from the telecoms infrastructure, 23% from the data centers, and the remainder comes from the end users themselves. It is the energy costs of this infrastructure, in particular the costs associated with the routers and switches, that I'm going to look at. One of the main disadvantages with current architecture is the networks are always on, consuming close to full power 24/7, irrespective of the load level. Currently, networks have no features to enable unused parts to shut down and go offline. Hence, the internet is using nearly the same amount of electricity at 6 in the evening when it experiences some of its highest levels, as 6 in the morning when it experiences some of its lowest periods of use. A potential solution to this problem is a minimal energy network, one in which only the minimal amount of links required to serve traffic are active. Hence, the rest of the links can be powered off or put into a low power state. To help me achieve this, I'm going to use a tool known as software-defined networking. In terms of hardware, a software-defined network is similar to a conventional network, with a variable amount of switches and routers all connected together. However, in a conventional network, while the intelligence is distributed among each switch, in a software-defined network, the intelligence is centralized in one server. If we take a look at a conventional switch, we can see that in terms of its operation, there are roughly two main elements. The first is a control plane, which collects information about the network and builds its own version of the topology map. It collects and stores all this information about the network itself and then makes forwarding decisions about where to route the traffic. The second part is the data plane, which takes care of all the packet forwarding. This plane deals with deciphering incoming packets, extracting information from them, and querying the control plane. It then takes instruction from the control plane on where to send the packet and forwards it out the appropriate port. In software-defined networking, these two planes are abstracted and separated. The forwarding plane remains within the switch, while all of the intelligence contained within the control plane is centralized. A secure channel needs to be maintained between the switch and the controller to ensure that they communicate properly and in real time. At first glance, this may seem counterintuitive, as you're taking away the redundancy that was found by having distributed architecture and introducing a single point of failure that could cripple the network. In addition, we are introducing another potential point of failure in the link between the centralized server and the switch. These risks can be mitigated by having a backup server ready to take over from the main server in the event it becomes faulty or malfunctions. In addition, many OpenFlow switches are designed with a conventional control plane included. This control plane can be configured to take over in the event that the software-defined networking controller fails to communicate with the switch. Even with these disadvantages, the potential savings to be gained from making these changes are numerous. We gain consistency among all the switches, as there is no chance of several of them having a different view of the topology. There is less computation power required, as only the central server makes intelligent decisions. All of the switches act dumb, following its instructions blindly, and can be designed at a lower spec. Routing decisions can be made relative to the state of the entire network and each switch in real time. There is less need for extensive link state messages to flow across the live channel. Most importantly, software-defined networking allows us inside the switch. We can write our own control software for the switch rather than having to rely on manufacturer's firmware. Even if software-defined networking has many other problems, this factor alone makes it worthwhile to implement. The actual implementation of software-defined networking that I use is OpenFlow. It is the only software-defined networking example to have received significant investment and begin commercial deployment. OpenFlow defines the protocol used for communication between the switch and the controller. OpenFlow is quite a strict implementation of software-defined networking, where the switch can only store information on how to handle packets for short periods of time. In its starting state, the switch contains an empty forwarding table. Hence, if it receives any packets, it has to refer the header to the controller. The controller will then make the routing decision for the switch and install a flow entry in the switch's forwarding table. This flow entry will contain instructions on how to forward the packet as well as timeouts, matching criteria and counters. There are usually two timeouts, one for idle behavior and an absolute timeout after which the flow is removed. The matching criteria has several levels of strictness. Any packet that matches the criteria for this flow before the timeout expires is then forwarded according to this without the controller being referenced. It will also install the flow in all subsequent switches the packet is likely to encounter. Hence, OpenFlow switches can be compared to a computer cache, with all the routing information residing on the central server and only the most recently used or often used information residing on each switch. Hence, the switch can process packets and look through its table at a much greater speed. OpenFlow has already been put to experimental use in Flowvisor for switch-level network virtualization. Here, several different control programs can be run on the same physical network, each acting as though it has its own network. The centralized server takes care of dividing bandwidth between each guest OpenFlow controller's network and deciding which controller packets belong to. Elastic Tree is another project where OpenFlow is used to scale the network relative to the traffic load flowing over and through the network. As can be seen in this video, it is a good representation of the always-on problem, as the network is always consuming the same amount of power regardless of the traffic level, which is being smoothly increased and decreased between the maximum and minimum amounts. When an OpenFlow controller is enabled, it has the ability to shut off parts of the network and reduce the power consumption steps matching the traffic levels. To realistically test networks, we use a tool called Mininet. This enables the virtualization of large networks through OS level virtualization. Here the entire network is run from one OS kernel, which keeps the overall memory cost low. In normal virtualization, each host or node would have its own file system, which can result in memory running out after relatively few nodes have been started up. It should be noted, however, that this was still virtualization and not simulation, and we have not actually created namespaces and virtual Ethernet pairs, so it still does provide realistic performance. I chose to implement my experiments on a factory network as it gave multiple redundant routes between nodes, which enable the network to be scaled to traffic demand relatively easily. There are several controllers that have been created to work with OpenFlow. Here is a list of them. The first three are linked together and were all developed from Nox Classic, which is a Python C++ combination controller that attempted to get speed from a core C++ and enabled easy functionality and modification by allowing extensions in Python. However, it produced suboptimal performance, as can be seen in the graphs on the left. Hence, the controller is split into two separate controllers, a pure C++ controller Nox for performance, and an experimental POX controller that allowed easy modification using only Python. I selected POX. Here you can see a rough layout of my controller with respect to Mininet on the bottom and POXDESK GUI on the top. My controller consists of four main modules. Discovery is only used at the start to send link state messages between all switches to discover the available links. Forwarding is the actual intelligent implementation of a controller and decides how packets should be routed through the network. Flow stats records the traffic levels being experienced by the network and reports back to forwarding. Forwarding is based upon a highly modified version of the Floyd-Warshall algorithm. My first experiment concentrated on examining the potential savings from integrating power management states into commercial OpenFlow switches. OpenFlow can then be used to control the switches and only power up the switches within its minimal energy network as needed to process traffic at different speeds. As you can see in this video, turning on a conventional switch causes most of the power consumption to begin. With all of the links connected but idling, the power consumption rises to within 5% of its final value. Hence, this is a contributing factor to the non-scalability of network power consumption. Hence, I have looked at the power consumption values for the D-Link Eco switch, which scales power relative to the amount of traffic flowing through it. This is not an ideal switch to use as it is designed for small-scale applications and mainly the at-home market rather than the commercial network. I chose it because it is the only switch available today that has a scaling ability. Using MATLAB, the power consumption levels of the switch were applied to the test network. I then ran the following test procedure on the network, both with and without the modified controller. The modifications to the controller consisted of integrating the additional flow stats component, and based on the level of traffic flowing through each switch, it assigns a state to the switch. Based on this experiment, I collected the following results for the 24-node network. Note that the graph does not start at 0 at the bottom. We can see a 41.5% reduction during periods of high usage. The network initially reaches a peak during setup, as configuration messages flow throughout the network to discover the topology. In reality, this level cannot be achieved as individual switches and links form natural bottlenecks, so even at full traffic, the network will never have this amount of traffic. Hence, there's already a significant saving that can be made from scaling the network. When the experiment is repeated on a larger 65-node network, these are the results that are obtained. Power saving rises to 48%, signifying that with a larger amount of nodes and large networks, more and more savings can be made by scaling it. My second experiment looked at assigning a path weighting based on the energy efficiency of the switches themselves. This resulted in a further saving of 6.25% compared to experiment 1's results. Hence, there are significant savings to be made from implementing energy-conscious scaling into network design.